Now we're going to move on to logarithmic functions, and here, what do we know about logarithmic functions and exponential functions? They are inverses, right? So you remember your inverses. We remember inverses reflect across this line, y equals x. Do you agree? Everybody remember that? So when we graph this function, remember that's the exponential function, yes? Remember that your initial point would be what a is, and in this case a has to be 1, doesn't it? Since it's not there. So we know we're going to start at 0, 1. Do you agree? And we know that it approached the horizontal asymptote at y equals 0, and it went up and to the right, correct? That's our exponential function. Well, if this one is the logarithmic function, and it's the inverse, we know that this would have to have the point 1, 0. Is that correct? Because inverses have the x and the y switched, yes? So your exponential function has a horizontal asymptote at y equals 0, right? So what do we know about a logarithmic function? If you're talking about inverses here. Yeah, you're going to have a vertical asymptote at x equals 0. And so this is going to be approaching that vertical asymptote, and this is going to be going up and to the right. So this is y equals log base b of x. This is y equals b to the x. And when we look at that identity function, y equals x, you can see those reflect across that line, correct? Yes? Does that make sense? So you can see where those inverse functions are. Okay, if we have y equals log base b of x, you can change this to exponential form. Do you guys remember in Algebra 2 how you changed it? You went your base to this power, and it will equal whatever's over here. Do you guys remember that in Algebra 2? Switching it from logarithmic to exponential form. And in the same sense, we can go from exponential form to logarithmic form by saying we know the base is the base always, right? So log base, exponential base, it's always going to be a base of x equals y. So being able to go from this to this and from this to this is super important. Questions? Okay, a couple things to remember. If you just have log of x, what is that base assumed to be? If there's no base given, it's base 10, correct? You remember that? And if we have natural log of x, we've talked about this a little bit already. Natural log is the same thing as saying log of base e of x. So these two are the same. These two are the same. So here's some basic properties that we need to remember. Log base b of 1 equals 0, which makes sense if we change it to exponential form, because anything to the 0 power does equal 1, doesn't it? Here, log base b of b equals 1, which makes sense because if we change that to exponential form, we'd have b to the first equals b. Here, log base b of b to the y equals y. Well, b to the y equals b to the y, yes? Change that to exponential form. So anytime these two match, your answer for the logarithm would just be the exponent there. And here, those two, if these two bases are equal, then it will equal this right here. And the way that we could make sense of this is an exponential equation, right? So to change that from an exponential to a logarithmic, you would have log base b of x equals the exponent, which is log base b of x. Yeah? And this is just saying the same thing with natural logarithms. Remember, ln is the same thing as saying log base e. So it doesn't matter what your base is. If you have 1 here, it's always going to be 0 because anything to the 0 power is 1. Same thing with this. Here, log base b of e. When these two match, it's just your exponent. Same thing here. Just remember that ln can be rewritten as log base e. Make sense? Here, this is the same thing as saying e to the log base e of x. And there, your exponential base, your logarithmic base are the same, and therefore it simply equals x. So those are just some properties, some basic properties that you learned in Algebra 2. So that's a quick review of it, right? You do have to know those properties, yeah? Looking at A. Here, it says give a reason for the following. It tells us that log base 2 of 8 does equal 3. So there's two different thoughts here that we could go with. We could change this to exponential form by doing 2 to the third power equals 8, which 2 to the third power does equal 8, right? Or if we wanted to talk about it in logarithmic form, log base 2, what is 8 in terms of a base of 2? 2 to the third power, right? And so when you have these two equal, it just equals your exponent. So you can see how that is true. Here, if you change this to exponential form, you'd take 3 to the 1/2 power, and that would equal the square root of 3. Well, square root of 3 is 3 to the 1/2. Yes, that's the same thing, yes? Do we understand that? Rational exponents, yeah? Okay. If we think in terms of the logarithmic form, we just said the square root of 3 is the same thing as saying 3 to the 1/2. And if these two match, it just equals that exponent. Looking at C. Here we would take 5 to the -2. And this equals 1 over 25. But isn't 25 5 squared? Yeah? And if we need it to be in the numerator, we simply just make that exponent negative, don't we? Fair? Or if we think of it this way, log base 5 of 1 over 5 squared is the same thing as saying log base 5 of 5 to the -2, which equals -2. Does that make sense? Here, if you change that to exponential form, 7 to the first power is 7, yes? if we look at this one, this is an exponential form, right? So if we wanted it in logarithmic form, we would take log of the base, so log base 6, sorry, of 11 equals the exponent, which is log base 6 of 11, correct? Okay, looking at the table here. It says logarithmic functions and inverse functions are inverse functions of exponential functions, meaning the x and the y are switched. So let's look at this table here, and let's look at f of x first. If we replace x with -2, we get 2 to the -2. Do you agree with that? To get rid of a negative exponent, we would move that to the denominator. True? And that would give us 1 over 4. Is that fair? So in f of x, when x is -2, y is 1/4. Is that true? So in the inverse function, what was our y becomes our x. And so if we think of it that way, here log base 2 of 1/4, well, I know 4 is 2 squared. Do you agree with that? And log base 2 of 2 to the -2 if I move it to the numerator. So what would this equal? -2, correct? So for my inverse function, when x was 1/4, my y was -2. Yes? All right, let's look at this one. Here we would have 2 to the -1. Well, to get rid of the negative, we move it to the denominator, correct? So when x is -1, y is 1/2, right? Because we have to move the 2 to the denominator to get rid of the negative exponent.
Yeah.
Does that make sense? So now, for our inverse function, the x would be 1/2. Everybody agree with that? So we'd have log base 2 of 1/2. Well, we know that we need that 2 in the numerator. So when I move it to the numerator, I have to have a -1 for my exponent, don't I? And that tells me when these two match, it would equal the exponent, which is -1. So for my inverse function, when x is 1/2, y is -1. And you can see those points are inverses, right? X and y are switched.
Why does that equal -1?
Because if we have 1/2, we have to move the 2 to the numerator so that we can have the same bases. And to move it from the denominator to the numerator, we have to add a negative exponent. And so when you have these two that match, it's equal to your exponent. Here, when x is 0, we know anything to the 0 power is just 1. So we have the point 0, 1, right? And if 1 is my y, 1 is my x and my inverse, and I'd have log base 2 of 1. And anytime you have a 1 here, what does that equal? Huh? Anytime you have a 1 here, what does that equal? because anything to the 0 power is 1. So it doesn't matter what your base is. If you're taking log of 1, it's going to equal 0. Yes? So here we're taking log base 2 of 1. It equals 0, which means we have the point 1, 0. Think of that in exponential form. 2 to what power gives you 1? 2 to the 0 power gets you 1. Yeah? Okay. Plugging in the 1, we'd have 2 to the first power. What's 2 to the first power? So we'd have the point 1, 2. And if your y is 2, your x is 2 for your inverse function, right? And if we think about log base 2 of 2, when these two match, it's just your exponent, which is 1 in this case, right? So we have the point 2, 1. You can see those are inverses. Here, if we look at 2, 2 squared is 4, and so we have the point 2, 4. And if this is my y coordinate, it becomes my x coordinate of an inverse, right? And if I have log base 2 of 4, I can change that to log base 2 of 2 squared, right? And when these two match, it's always going to be your exponent. And therefore, you have the point 4, 2. And so you can see those inverse functions there. So 2 to the x and log base 2 of x are inverse functions. All right, the logarithms with base 10 are called common logarithms. That's the log that you'll see on your calculator. That is base 10. It's often dropped, and if there is no base, it is understood to be base 10. So in this case, this is log base 10. Well, if I could get 100 in terms of 10 to some power, I can evaluate that pretty easily, can't I? 10 to what power gives me 100? Right? 10 times 10 is 100, yes? However many zeros there are, that's your exponent, correct? And so here, when you have these two match, it just equals your exponent. When you think of this one, this is log base 10 of 10 to what power? What's the square root in terms of a rational exponent? Remember, the square root is just to the 1/2 power. The cubed root is to the 1/3 power, yes? Remember going from radical to rational form? Yes? If you have the square root of x cubed, that is x to the 3/2, correct? If you have the cubed root of x to the 5th power, that is x to the 5/3. This is your index, this is your exponent. Do you remember that? So here our bases match and we would just get 1/2. Here, this would be log base 10 of 1/10 to what power? Third, right? 10 times 10 is 100, times 10 is 1,000, yes? However many zeros there are there, that's what's going to be your exponent. Now, not necessarily true if it's 0.000, right? You got to take that into consideration because you got to move an extra value over. So, log base 10 of 10 to the -3rd, right? Because we got to move that up. And so now your bases are the same, so this just equals the exponent of -3. Here, if we look at this logarithm, log base 6 of 6, When these two match, it's equal to your exponent, isn't it? Which is, so this is the same thing as saying 10 to the first power, which is just 10. The next piece says to evaluate them with a calculator. Well, when you're doing that, you just use that log button on your calculator. I got 1.53781 and it just kept going, right? In this class, we're going to go to 3 decimal places. So I would accept 1.537 or 1.538. This is rounded, this is truncated, yes? So the reason we do this is because in AP Calc, it has to be accurate to 3 decimal places. That means that you could leave this whole thing because that's accurate to 3 decimal places, but they only read to 3 decimal places. So that's what we're going to practice. In other courses, college algebra, for instance, it's going to tell you to round to the nearest hundredth or tenth, or it might be significant digits. And if it was significant digits, that's how many? 3. And so it would have been 1.54. Yes? Okay. Looking at the next one, log of 0.43 gives me negative 0.36653, and it just kept going. So negative 0.366 or negative 0.367 would be appropriate. So if it doesn't tell you where to round, this is what we're doing, yes? What happens with this one? What does it tell you? What does the error say? Yeah, this is not real, right? This is in real mode. And this would be a not real answer. Well, why is that? Think about your graph of a logarithmic function. Does it ever cross where x is 0? No. So it will never be defined if it is negative, correct? So the general statement there, logarithms are not defined for negative values of x. Or better yet, what's the domain of a logarithmic function? Not including 0, right?
Yep.
Do we understand that? Questions? Solving simple logarithmic equations. Well, it says solve each equation by changing it to its exponential form, right? What's the base here? The base is 10 because it's understood to be 10 if there's nothing there, right? Changing it to exponential form would be taking the base to this power, so 10 to the third power, and it equals whatever's here, yes? X. So what does x equal? 1,000. Looking at this one, we take our base to this power, and it equals whatever's here. So 2 to the 5th power, and it would equal x, correct? Which means what's x equal? 32. Remember that ln and log base e are the same, yes? So when we're evaluating this, you can think of log base e of e to the 1/2, right? So what would that equal? 1/2. Here you can think of this as log base e of e to the 5th power, yes? And when those match, it's just your exponent, correct? Here, this is the same thing as saying e to the log base e of 4, and when your exponential base and your log base are the same, just equals whatever is right here, correct? Questions there? For this, it's the same thing. You're just using ln instead of log. So right below it is your ln. This gives us 3.157000, and it just kept going. So 3.157 would be the only accurate answer there, yes? Here, ln of 0.48. Negative 0.733969. If we look at 3 decimal places, that would be negative 0.733 or negative 0.734. And what do we know about this one? It's not defined, right? It's not in the domain. Because it doesn't matter what your base is, the log of any negative number is not defined. All right, last 4 here. Evaluate the natural logarithms below. Well, we know this would be log base e of e to the 7th power, which would give us, here we know this would be e to the log base e of 81. When those bases match, it just equals 81 in this case, yes? Here, this is the same thing as saying e to the log base e of the square root of 9x. Again, your bases are the same, so this would equal the square root of 9x. Or could we simplify that? What's the square root of 9? So 3 square root of x, yes? And the last one for today, this is the same thing as saying log base e of e to the negative 5, right? Since we need to bring that up. Those match and we would get negative 5. So all that's left is the graphing of the logarithmic functions, and we will finish that up on